All right, I'm going to introduce you to the big idea for this unit. That's Taylor polynomials and why they might be useful. So let's first take a blast from the past here. And I'd like you to try to recall, and I actually want you to try to recall this, so go look this up somewhere in your notes. This is using a tangent line to approximate or to estimate the sine of 0.3. So this is that local linearization using a tangent line to approximate a value. Go look it up, see if you can solve this. Okay, so when we solve a problem like this, we think about a point that is conveniently close to 0.3, something that we know a little bit about when we're trying to write the equation of the tangent line. Because what I'm trying to do right now is, if I've got the graph for sine, and here's 0.3, I want to use a line tangent to that curve that will be really close to 0.3. So if I use this point here at 0, 0, because I know that's conveniently close, so my convenient point is 0, 0, because that's a point I know that's on the graph. So I'm going to write the equation of the line tangent to this graph at the point 0, 0, because then that line will be close enough to the curve to help me approximate 0.3. All right, so in order to write the equation of the line, first of all, I do know some information. I know the y1 and x1, so this is y minus 0 equals the slope, and then x minus 0. So I need to find the slope of that tangent line. In order to find the slope of that tangent line, I will need to find the derivative of sine x. Derivative of sine is cosine. And I'm going to find the slope at this particular convenient point, so the slope at 0. That would be the cosine of 0, which is 1. All right, so I've got enough now. I'm going to write the equation of my line. So this really just turns out to be y equals x is a pretty good approximation for sine x, as long as we're near 0. So the question then said, though, use the tangent line to approximate or to estimate the sine of 0.3. So we would say that the sine of 0.3 is approximately found by plugging 0.3 into the tangent line that we found. So that's 0.3. All right, so that's a blast from the past. That's the tangent line approximation, writing an equation of a line that's really close to that curve that can help us find other values on the function near that point. So what we've done in the past is what's called a Taylor polynomial. So let's go here. The tangent line we wrote is an example of a Taylor polynomial. A Taylor polynomial is a good approximation of a function on a specified domain. So that means this line that we drew is not a good fit for sine x everywhere. It's good on a small domain. So let's go look at the graph of sine x and y equals x on Desmos and see what that actually looks like. So I can see that that line is pretty close for some x values, but as soon as we reach, like, I don't know, not too far away from 0, the line starts to go away from sine x and is no longer a good approximation. So let's zoom in a little bit and let's see if we can get a decent approximation. So I can even see that at -1 and +1, already this is not a very good fit, because at -1, the blue line is really far away from the red line. How far away is close enough? It's a judgment call at this point. We're going to get more precise later. So we're going to make our judgment call. I'm going to zoom in just a little bit more. And to me, I would almost think like 0.3 maybe, but maybe 0.25. Let's see. Yeah, 0.25 is pretty close as well. So right now we're just making a judgment call. We can split hairs, but it looks like starting at about 0.3, those two lines start to diverge. Those two lines start to get far enough apart from each other that maybe we could have used a different point to write the equation of the tangent line. So I'm going to call this is the interval of convergence is what we call this. And I'm going to say it like 0.28 or 0.3 is a pretty good interval of convergence. And that's true on the other side too, because sine is a symmetric function, that if I look at 0.28 or 0.3 on the negative side, also a pretty close fit. So this is your call. I'm actually going to go with negative 0.25 now that I look at it. I'm trying to be precise here. So the closer I can get, the better. Okay, right now, I mean, don't panic about this part. This isn't anything that has to be precise right now. We're going to say that the domain for the tangent line to be a good approximation the tangent line, I need to add a little more specifics, the tangent line at x equals 0 to be a good approximation for f of x equals sine x is about, I'm going to go with negative 0.25. Now we just used it to approximate 0.3. And that's okay because we're getting close. So this isn't an exact science right now. We're just saying they're almost the same line up until negative 0.25 and positive 0.25. So what we call this is the interval of convergence. And it's just for this tangent line. It's going to change as we add more values to our polynomial. But we're saying we could use this tangent line at x equals 0 and be pretty confident between negative 0.25 and positive 0.25. Now, that being said, we used it to approximate 0.3, which is just outside of what we thought was a good fit. But it's a decent approximation. It's good enough for right now. Okay, so that's a slight intro. That's the very tip of the iceberg on Taylor polynomials. Let me give you some vocabulary now. So the tangent line that we just drew, we're going to describe it as a Taylor polynomial for f of x equals sine x of degree 1, because the highest exponent was the first power. It was y equals x to the first. This was centered at 0 because we used 0 as the convenient point. So this is a Taylor polynomial for f of x equals sine x of degree 1, centered at 0. Since the polynomial was centered at 0, we can also call it a Maclaurin polynomial. It's kind of like a square being a rectangle, but a rectangle is not a square. A Maclaurin polynomial is a type of Taylor polynomial. Is a type of Taylor polynomial. Oops. It is a subset of a Taylor polynomial because it is specifically centered at 0. So Maclaurin did a lot of research with Taylor polynomials centered at 0. So I'll use Maclaurin and Taylor polynomial interchangeably for polynomials that are centered at 0. Then they mean the same thing. But Maclaurin is more specific, and that is the only type of polynomial that's centered at 0. In other words, we used the point x equals 0 to write the equation of the line. All right, so let's see if we can get a little more specific, or a little bit closer to the sine x. I'm going to add terms on to that tangent line approximation for sine. So I have a degree 3, a degree 5, and a degree 7 Maclaurin or Taylor polynomial for approximations of sine x. I'd like you to pause this, and I'd like you to go graph sine x and then each one of these 3 polynomials to see what happens as you add more terms. Okay, I hope you actually did that, because I'm going to do it now and we're going to start taking a look. Because what I want you to do, I would like you to do is decide on an interval of convergence for each of these. I'll do the first one, but I'm not going to spend valuable video time talking them out. So I'll do the first one with you. But what I'd like you to do is decide upon, and you just have to make a decision. I mean, right now this is not an exact science yet. So don't panic about that part. Right now you're just saying, well, that's pretty close. I swear to you, we will find these things exact. So I'm going to graph the third degree polynomial, and I'm going to try to decide what is a pretty good interval of convergence. So I'm going to go there, x minus, oops. I'm going to just add on to what I had, minus x cubed divided by 6. Okay, that looks like a really good fit. So I'm going to zoom out a little bit more. I'm going to get rid of this so I can see a little bit more of my curve. Well, that looks like a decent fit up until like maybe 1.5. So let's go look in here. And of course I'm not using radians, and that's horrible, and I get all of that. And since this is symmetric, I'm only going to look at the positive side. It's looking like a pretty good fit up until 1. Even 1.05 is pretty close. So in here, this is a judgment call. I'm actually going to say, I mean, if I'm looking at, to try to be precise, I'm going to say either 1.05 or 1.1. Because I know that the more terms I add, the more precise I'm going to get. The closer this curve is going to fit to sine x. So I'm going to go with 1.05 to stick with precision. And if you look, I just added on one more term to the polynomial, and this curve is starting to fit sine x so much better. And I think that when you graph the others, you're going to start to see a really interesting development. So let's go back. 1.05 is what I said. So I would say the interval of convergence for this third degree Taylor polynomial is about from negative 1.05 to positive 1.05. I'd like you to go do the same thing for the fifth and the seventh degree polynomial. Okay, I hope you were able to make a decision, and you just have to call it at whatever you feel is the most precise. It's okay right now. And I hope that you saw that once you got to the seventh degree polynomial, this equation that we're writing, is really starting to fit the sine curve really well on a larger domain. So I hope you're wondering, where on earth do these terms come from? So I just gave you the third degree, I gave you the fifth, I gave you the seventh, and you'll notice that the third degree polynomial is also included in the fifth degree polynomial. So I just took the third degree and added on another term. Then I took the fifth degree and added on the seventh power. So what I'd like you to do is kind of notice the pattern here. Can you now write a ninth degree Maclaurin polynomial for sine x? Based off the patterns you're seeing here, can you write a ninth degree polynomial and tell me over which domain does this polynomial converge to sine x? And then tell me if you can write out the general expression for any term in the Maclaurin polynomials for sine x. So this one's going to take you a little bit of time. You actually need to pause and go spend some time on this. See if you can write that ninth degree Maclaurin polynomial and then come back. Okay, I hope you just did the ninth degree. Let's just do the ninth degree together. So we know that sine x, and the way we write this is pretty specific, because we're saying that sine x is approximately, it's not exactly this ninth degree polynomial, but the ninth degree polynomial is a good approximation. And this ninth degree polynomial is equal to, and we'll just start writing out the terms, x minus x cubed over 6 plus x to the fifth over 120. Now I hope you started to realize where those denominators were coming from. Remember back in the day I said you need to really recognize these numbers? Well, this is it. Because what I'm noticing, and I hope you did as well, is that this first term is x to the first over 1 factorial. The next one is x to the third. This is 3 factorial. 3 times 2 times 1. And then this is x to the fifth, 5 factorial, minus x to the 7th, and this is actually 7 factorial. So I know now, following this is positive, negative, positive, negative. This next term is positive x to the 9th over 9 factorial. Sorry, I didn't even calculate that one. I should have, but I don't know. Over 9 factorial. So there's the 9th degree polynomial. Can you write now a general expression for any term in this Maclaurin polynomial? So if I said, what is the 11th degree term? So it would be the 1, 2, 3, 4, 5, the 6th term. So what would this term be without knowing the term before it? Can you write a general expression? So if you haven't done that already, pause, see if you can write that general expression. Okay, I'm going to start with the exponents first. We've talked about this before. They're all odd exponents. And remember, we're going to start with n equaling 0. So I'm going to say that since these are odd and n starts with 0, I know that the numerator will be 2 times n plus 1. 2 times 0 plus 1 is 1. 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5, and so on. The denominators are exactly the same. They're also the odd values, but in factorial style. And then finally, looking at the fact that this oscillates between being positive and being negative, knowing that the first term needs to be positive, you can write this anywhere, but I'm going to just put it out in front for right now. If I say negative 1 to the n is 0 to begin, so negative 1 to the 0 power is positive 1, negative 1 to the first is negative. So this looks good. This looks like so this is one way to write it. You can write it off to the side. You can write it like this. But this is the general term for the general expression for any term in a Maclaurin polynomial for sin x. All right, let's wrap this up then. This is something you're just going to have to know. This Maclaurin polynomial for sin x is something you have to have memorized. It's something you need to recognize at any moment in time. So here is the Maclaurin polynomial that converges to sin x, and we're saying equal to in this case. And the reason we say equal to, if you were to graph out an infinite number of these terms, the interval of convergence for this Maclaurin polynomial to sin x is from negative infinity to infinity. This polynomial is a perfect match for sin x at every value of x from negative infinity to infinity. It's pretty amazing. Now I'm hoping you're wondering, like, what the heck, why do we even bother finding these polynomials? There is a reason for this. Computers have a difficult time with sin x or exponential functions, but repeated multiplication, like in a polynomial, x to the 3rd power is just repeated multiplication, 5 times 5 times 5. A computer or a calculator can handle that no problem. So a lot of times, for example, in a GPS, in order for a GPS to track where you are, it uses a Taylor polynomial. So it plots points of where you are and uses a polynomial to map your location. And so when you talk about a GPS that's good between like plus or minus 1 meter, which is a horrible GPS, but saying, oh, this GPS is good between, as long as you're within 3 meters of somebody. Well, that's because that's as far out as the Maclaurin polynomial or Taylor polynomial went. It only goes out so many terms because that's all the computing capability of that GPS. So they're saying, is going out to just a few terms, we're going to get you close, but the interval of convergence of what we did for your location, you're going to be good within a couple feet. So that's one use for Maclaurin or Taylor polynomials, is for a way for computers to calculate things quickly, especially if we get into exponential functions or trigonometric functions. And we'll talk more about this in many more videos to come.